Out of all the weird things that we tell you in chemistry, I think this is probably the weirdest, and if it's not, it's at least in the running. The Heisenberg uncertainty principle. What this is saying is we can't know where something is and where it's going at the same time. And if we try to know both, we're going to have trade-offs between the quality of each of those measurements. Now why? Well, it's because the electron is acting both as a wave and as a particle. Makes it really challenging for us to try to understand both simultaneously, and in fact, we can't. We can come to some best answer for it, but we can't know both simultaneously. Let's take a look at an equation that represents this. Now this thing looks pretty hairy, I'll expect. So let me break it down a little bit. We have our uncertainty in our position, delta x, and we have the uncertainty in momentum. And we would like those two to be very small. We'd like to have no uncertainty in either things, right? But it turns out that no matter what we do, we can never get any better than Planck's constant divided by 4 pi. Okay, that's not very descriptive, and I know it. But that's okay, because the key thing to recognize here is this is going to be some sort of a constant. Planck's constant divided by 3.14 divided by 4 gives you a value. These uncertainties times the mass will always be greater than or equal to this value. We can never get these uncertainties to be so small that we get below this number. Now, we can get those uncertainties to be much, much smaller if we have a really large mass. But with an electron, we're at a pretty small mass. So those uncertainties are going to be fairly large all the time. Now this is what that value looks like. If we go ahead and we just solve this, we'd get this constant. You see we're in meters squared times kilograms divided by seconds. We can never know speed and position better than that for any object at all. Now, it doesn't matter for really heavy objects like I just mentioned. If it's really heavy, these two values can be very small and we still don't violate that rule. So if it's bigger than a subatomic particle, not an electron. Oh, was that in my throat? Yeah, the electron. For bigger than an electron, it's probably not going to matter much. But when we're talking about the electron, it's a really, really critical thing. We can't know where it is and where it's going at the same time. Now, I also want to point out, this is on top of the de Broglie wavelength. So, in de Broglie wavelength, we say the electron is actually spread out in space because particles actually do act as waves, as we showed way back with our double slit experiment. We saw that electron beams can actually interfere with each other, just like photons do. They have a wavelength. So there's this wavelength where we don't know where the electron is. It's actually spread out in space. I guess we know where it is, but it's spread out in space. On top of that, we don't know exactly where it is or where it's going. So how do we deal with that much uncertainty? Two different physical phenomena making it so we can't tell you what's going on with the electron. Here's what we're going to do. We're going to stop talking about those nice circular orbits. You know, the ones where we say our nucleus is right here. We had one ring right here, another ring like this, and that was our Bohr model. Or we have them kind of with the rings kind of off center to each other, or tilted to each other, I should say. You've seen that sort of a model before. We're going to go even further than that. We're going to stop talking about orbits. We're going to talk about something called orbitals. And there's an important distinction to be made between them. And also point out, we're not really going to talk about orbits anymore. From here on out in the course, we're talking about orbitals. An orbital is an area of high probability where we're probably going to find the electron. Now, probably means somebody should ask how probable is that we'll find it there. So what we're going to do anytime that we look at an atom or a picture of an atom or a molecule, and we're trying to picture what's going on there, we're going to decide how probable we're going to call the electron. Now, if we want to be absolutely certain that we know where it is, since we can't know where it is, that means we have to go all the way out from our nucleus out here to infinity. We have a 100% chance of finding the electron somewhere between the nucleus and infinity. No kidding. That's not very helpful, is it? Well, what if we trim that down? What if instead of going out to infinity, we only go out to 90%? chance of finding the electron. That's going to actually be a lot more tractable, and it's something we can deal with a lot when we're dealing with our drawings. Now, there's still going to be a 10% chance that the electron is at that moment somewhere else in the universe. And yes, somewhere else in the universe, if I'm talking about something here on Earth, it's probably not past Neptune. It's probably not past Mars. Probably. But there is a minuscule chance that it's that far away, even though it's associated with an atom that's right here on Earth. Now, is that violating speed of light? I'm going to call there be dragons again. That's so far off of the map that there probably is an answer to it, but you aren't going to find it in Chem 1, and it's not going to be relevant for Chem 1. You have to go to some fancy calculus and some fancy physics to explain those sort of things. And that's when you start having fun with entanglement and all that good other stuff. We're not going out to infinity. We're typically going to cut things off at the 90% level. But always remember, there is still a non-zero chance that the electron is someplace else. In fact, there's a pretty good chance the electron is somewhere else. So have that in mind as we're talking about these shapes.